Space and Science News. With James. In the inky blackness of space, our moon hangs silently, a constant companion to Earth for billions of years. But beneath its dusty, cratered surface lies a secret, one that could change the course of human space exploration forever. For decades, scientists have speculated about the presence of water on the moon, but recent discoveries have blown those theories wide open. Today, we'll be talking about NASA's LRO lunar ice deposits because why not? It's only the most exciting lunar discovery in recent history. Imagine vast reserves of ice hidden in the eternal shadows of lunar craters, just waiting to be tapped. This isn't just a drop in the bucket, we're talking about potential lakes worth of frozen water. What's even more astonishing is that this ice isn't confined to the South Pole. It's spread far and wide across the lunar surface, lurking in places we never thought to look. The implications of this discovery are nothing short of revolutionary. Get ready, space enthusiasts. We're about to embark on a journey that will transform your understanding of our celestial neighbor. Are you prepared for some surprising revelations? Let's dive deep into the subject of lunar ice deposits and uncover the secrets that have been lurking just above us. In the vast expanse of our cosmic neighborhood, the moon has long been a subject of fascination and scientific inquiry. For decades, researchers have speculated about the presence of water ice on our celestial companion. Now, a groundbreaking study using data from NASA's Lunar Reconnaissance Orbiter, LRO, has revealed that lunar ice deposits are far more widespread than previously thought. This discovery has sent ripples of excitement through the scientific community and space exploration agencies worldwide. The moon, once thought to be a dry and desolate world, is now showing us a different face. Hidden in the shadows of its craters and valleys, water ice has been quietly accumulating for billions of years. This isn't just a scientific curiosity, it's a potential game-changer for future lunar missions and our long-term plans for space exploration. Water, after all, is one of the most crucial resources for sustaining human life and enabling long-duration space travel. As we delve into the details of this remarkable finding, we'll explore how this discovery was made, what it means for our understanding of the moon, and how it could shape the future of space exploration. The Lunar Reconnaissance Orbiter, launched by NASA in 2009, has been tirelessly mapping and studying the moon's surface for over a decade. Its suite of sophisticated instruments has provided us with unprecedented insights into our nearest celestial neighbor. Among these instruments, the Lunar Exploration Neutron Detector, or LEND, has played a crucial role in uncovering the moon's icy secrets. Dr. Timothy P. McClanahan of NASA's Goddard Space Flight Center led a team that analyzed data from LEND, focusing on areas known as permanently shadowed regions, or PSRs. These are areas, typically found in deep craters near the lunar poles, that never receive direct sunlight due to the moon's tilt and topography. The team's findings, published in the Planetary Science Journal, have expanded our understanding of lunar ice distribution. Previous studies had identified ice deposits in large PSRs near the lunar South Pole, including well-known craters like Cabeus, Hayworth, Shoemaker, and Faustini. However, the new analysis reveals that water ice is present in PSRs much farther from the pole than previously thought, extending to at least 77 degrees south latitude. This means that the potential for water ice on the moon is significantly greater than we had imagined. The study doesn't just confirm the presence of ice, it also provides valuable insights into where we're most likely to find it. Dr. McClanahan and his team found that the highest concentrations of ice are expected in the coldest parts of the PSRs, where temperatures plummet below 75 Kelvin, or about -198 degrees Celsius. These frigid conditions, combined with the perpetual darkness, create perfect preserves for water ice. Interestingly, the research suggests that for every square meter of surface area over these deposits, there could be at least 5 liters of ice within the top meter of the lunar regolith. This estimation, while not definitive, gives us a tantalizing glimpse of the potential water resources waiting to be tapped on the moon. To understand how scientists detected ice on the moon, we need to dive into the fascinating world of neutron detection. The LRO's LEND instrument, specifically its collimated sensor for epithermal neutrons, (SEN), played a crucial role in this discovery. But how does measuring neutrons tell us about water ice? The answer lies in the cosmic rays that constantly bombard the moon's surface. When high-energy galactic cosmic rays, originating from powerful events like exploding stars, hit the moon, they interact with atoms in the lunar regolith. This interaction creates a shower of particles, including neutrons. These neutrons then bounce around within the top meter or so of the lunar surface, occasionally making their way back into space. It's these escaping neutrons that LEND detects. Here's where it gets interesting. Hydrogen, a key component of water, has a unique effect on these neutrons. Because hydrogen atoms have roughly the same mass as neutrons, they're particularly effective at slowing down neutrons through collisions. This means that in areas where there's a lot of hydrogen, potentially in the form of water ice, we see fewer moderate energy, or epithermal, neutrons escaping. The SEN has a fixed field of view of about 30 kilometers in diameter. By mapping out where it detected fewer epithermal neutrons, the research team could infer the presence of hydrogen-rich areas, likely indicating water ice deposits. But the analysis didn't stop there. The team developed a sophisticated model to account for the varying sizes of PSRs and how they would appear to the instrument. Dr. McClanahan and his colleagues hypothesized that if all PSRs had the same hydrogen concentration, the amount of hydrogen detected should be proportional to the area of the PSR. They tested this hypothesis using data from 502 PSRs, ranging in size from just 4 square kilometers to over 1,000 square kilometers. As expected, they found a stronger correlation between area and hydrogen detection in larger PSRs, while smaller ones showed a weaker relationship. This methodical approach allowed the team to map out not just where ice is likely to be found, but also where it's less likely to accumulate. They discovered that warmer areas that receive periodic sunlight are less likely to harbor significant ice deposits. This makes sense, as exposure to sunlight would cause the ice to sublimate and be lost to space. The study also sheds light on how this ice might have gotten there in the first place. There are several possible sources. Comets and meteors impacting the moon could have delivered water directly. Alternatively, hydrogen from the solar wind could have combined with oxygen in the lunar regolith to form water molecules. Another possibility is that water vapor could have been released from the moon's interior through volcanic processes. Once formed or delivered, water molecules on the lunar surface lead a precarious existence. They can be dislodged by meteorite impacts, space radiation, or sunlight, causing them to hop across the lunar surface. Many are lost to space, but some lucky molecules find their way into the cold traps of PSRs. Here, in the perpetual darkness and extreme cold, they can remain stable for billions of years, slowly accumulating into the deposits we're now discovering. The discovery of widespread ice deposits on the moon is more than just a scientific curiosity, it has profound implications for the future of space exploration. Water is often called the oil of space, due to its crucial importance for sustaining human life and enabling long-duration space missions. The presence of accessible water on the moon could revolutionize our approach to lunar and deep space exploration. First and foremost, water is essential for human survival. Future lunar bases would need a reliable source of water for drinking, hygiene, and growing food in hydroponic systems. Transporting water from Earth is extremely costly, with some estimates suggesting it could cost up to $50,000 per kilogram to ship resources to the moon. Having a local source of water would dramatically reduce the cost and complexity of establishing a permanent human presence on the lunar surface. But the potential of lunar water goes far beyond direct consumption. Water can be broken down into its constituent elements, hydrogen and oxygen, through a process called electrolysis. This has several exciting applications. Oxygen, of course, is crucial for breathing, but it's also a key component of rocket fuel. Hydrogen, when combined with oxygen, creates an extremely efficient propellant. This means that the moon could potentially serve as a cosmic gas station, allowing spacecraft to refuel for journeys to Mars and beyond. The oxygen derived from lunar water could also be used in life support systems and for manufacturing processes on the moon. Meanwhile, hydrogen has potential applications in energy storage and power generation through fuel cells. These capabilities would be crucial for establishing self-sustaining lunar colonies. Moreover, the presence of water ice could support scientific research in various fields. Studying the composition of this ancient ice could provide insights into the early solar system and the origin of water on Earth. The polar regions of the moon, where much of this ice is found, could also serve as ideal locations for astronomical observatories, shielded from Earth's interference and with a stable, cold environment for sensitive instruments. The widespread nature of these ice deposits, as revealed by this study, is particularly exciting for mission planners. It means that future lunar missions have more potential landing sites to choose from, increasing flexibility and safety. Different areas could be selected based on their specific ice concentrations and accessibility, tailored to the goals of each mission. However, accessing and utilizing this ice presents significant challenges. The permanently shadowed regions where the ice is found are extremely cold and dark, making them difficult and dangerous to explore. Future missions will need to develop specialized equipment capable of operating in these harsh conditions. This might include robotic explorers with advanced thermal management systems, or new drilling technologies designed to extract ice from the lunar regolith. There's also the question of how to extract and process the ice efficiently and sustainably. We'll need to develop methods that don't contaminate or deplete this valuable resource. This could involve in-situ resource utilization, ISRU, technologies, which are designed to use local resources for various purposes. As we look to the future, this discovery could accelerate plans for a permanent human return to the moon. NASA's Artemis program, which aims to land the first woman and next man on the moon by 2024, could benefit greatly from this new understanding of lunar ice distribution. International space agencies and private companies are also likely to factor this information into their lunar exploration plans. The discovery of widespread ice deposits on the moon marks a pivotal moment in our understanding of our celestial neighbor and the future of space exploration. It transforms the moon from a seemingly barren world to a potential oasis of resources, waiting to be tapped by future explorers and settlers. This finding is the result of years of meticulous observation and analysis, showcasing the power of long-term scientific missions like the Lunar Reconnaissance Orbiter. It's a testament to human ingenuity and perseverance, using advanced technology to uncover secrets hidden in the shadows of lunar craters for billions of years. As we've explored in this video, the implications of this discovery are far-reaching. It challenges our perceptions of the moon and opens up new possibilities for lunar exploration and utilization. The potential for using lunar water as a resource for sustaining human life, powering spacecraft, and enabling scientific research is truly exciting. However, it's important to remember that this discovery also brings new responsibilities. As we plan future missions to explore and potentially exploit these ice deposits, we must consider the ethical implications. How do we ensure that we use this resource sustainably? How do we balance the needs of human exploration with the preservation of the moon's unique environment? These are questions that scientists, policymakers, and ethicists will need to grapple with in the coming years. The widespread nature of these ice deposits also highlights the importance of international cooperation in space exploration. No single nation or organization can fully explore and utilize this resource alone. Collaborative efforts will be crucial in developing the technologies needed to access and use lunar ice, as well as in establishing guidelines for its responsible use. As we look to the future, this discovery ignites our imagination about what's possible. Could we see permanent lunar bases within our lifetime, sustained by local water resources? Might the moon become a stepping stone for human missions to Mars and beyond? Could lunar ice deposits hold clues to the origins of water in our solar system? These questions and possibilities remind us of the enduring value of space exploration. Each new discovery not only advances our scientific knowledge but also pushes the boundaries of what we believe is possible. The moon, our constant companion in the night sky, continues to surprise and inspire us. As we conclude, it's worth reflecting on how far we've come in our understanding of the moon. From ancient myths and legends to the first lunar landings, and now to detailed mapping of ice deposits, our journey of lunar exploration is a testament to human curiosity and determination. This latest discovery is not an endpoint, but rather a new beginning, opening up exciting new avenues for exploration and discovery. The widespread ice deposits on the moon represent more than just a scientific finding, they symbolize hope and possibility. They remind us that even in places we think we know well, there are still secrets waiting to be uncovered. As we continue to explore and learn, who knows what other wonders we might discover, not just on the moon, but throughout our vast and mysterious universe. As we conclude our exploration of NASA's groundbreaking findings on lunar ice deposits, it's clear that the moon holds far more than we ever imagined. The discovery of widespread ice, not just concentrated at the poles but across various regions, opens up a world of possibilities for future lunar missions. This resource could be vital for sustaining human life, fueling spacecraft, and even conducting scientific research that deepens our understanding of the solar system. The implications are profound. With the potential for in-situ resource utilization, we could establish a permanent human presence on the moon, paving the way for further exploration of Mars and beyond. Each new piece of information about lunar ice brings us closer to realizing these ambitious goals and transforming our vision of space travel. Thank you for joining us on this fascinating journey into the secrets of our moon. If you found this video enlightening, please give it a thumbs up and share it with fellow space enthusiasts. We'd love to hear your thoughts. What do you think about the potential for lunar ice? Are you excited about future missions? Don't forget to subscribe to our channel for more engaging content on space exploration and scientific discoveries. Hit that notification bell so you never miss an update. Together, let's continue to explore the wonders of our universe. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.